March 15, 1943. Shipdham Airfield, Norfolk, England. Captain James Hartwell stood in the equipment shed, staring at the modified bomb shackles that had just been installed in his B-24 Liberator. The metal fittings gleamed under the bare bulb hanging from the corrugated roof, still smelling of machine oil and fresh paint. His bombardier, Lieutenant Frankchen, crouched beside the assembly, running his fingers along the welds with the careful attention of a surgeon examining an incision. Neither man spoke, but both understood what these modifications represented. In 72 hours, they would attempt something the Army Air Forces had declared technically impossible. What happened in the skies over the Ruhr Valley that week would rewrite the doctrine of strategic bombing and force German military planners to confront a threat they had calculated could never materialize. The techniques Hartwell's crew would pioneer over the next month would increase the effective destructive capacity of the Consolidated B-24 Liberator by nearly 300%, transforming precision bombing from a theoretical concept into a systematic dismantling of Germany's industrial capacity. Before we jump back in, tell us where you're tuning in from, and if this story touches you, make sure you're subscribed, because tomorrow, I've saved something extra special for you. The mathematics of aerial bombardment had remained frustratingly consistent since the first strategic raids over Germany began. A standard B-24 Liberator carried a maximum bomb load of 8,000 pounds when configured for long-range missions deep into Reich territory. That load typically consisted of 16 500-pound general-purpose bombs or 8,000-pound high-explosive bombs, arranged in the bomb bay according to strict loading procedures that balanced weight distribution and ensured safe release. The bombs were mounted on vertical shackles that held them nose up in two parallel rows running the length of the bay. This configuration had been engineered by Consolidated Aircraft Corporation based on careful calculations of structural stress, aerodynamic stability, and safe separation during release. Every bombardier in the 8th Air Force had been trained on these specifications. Every bomb loader knew the procedures by heart. Every mission planner calculated target effects based on these fixed parameters. The system worked, but it was limited, and those limitations were costing lives and prolonging the war. James Hartwell was 26 years old when he arrived at Shipdham in January 1943 to take command of a B-24 crew assigned to the 44th Bomb Group, the oldest heavy bombardment group in the 8th Air Force. He had grown up in Duluth, Minnesota, where his father operated a commercial fishing operation on Lake Superior. The elder Hartwell ran a fleet of 6 boats, and young James had learned early that efficiency meant survival. On the lake, fuel economy determined whether a boat returned with profit or loss. Weight distribution affected stability in rough water. Mechanical reliability made the difference between a successful season and bankruptcy. Those lessons shaped how Hartwell thought about aviation. When he entered the Army Air Corps in 1940, he approached flying with the same practical mindset his father had applied to commercial fishing. Aircraft were tools with specific capabilities and limitations, but those limitations were often matters of convention rather than physics. Hartwell's path to command of a B-24 had been unconventional. He had washed out of fighter training in 1941, not because he lacked flying skill but because his instructors noted he flew too cautiously, calculating fuel consumption and engine temperature when other cadets were practicing aggressive maneuvers. The evaluation that ended his fighter career stated he lacked the aggressive instinct required for air-to-air combat. That same evaluation recommended him for multi-engine training, where his methodical approach proved ideal. He excelled in B-17 training, graduated near the top of his class, and was immediately assigned as a co-pilot in a Flying Fortress crew preparing for deployment to England. But 3 weeks before shipping out, Hartwell had volunteered for a temporary assignment that would change his trajectory. The Army Air Forces were converting several bomb groups from B-17s to B-24s, and they needed experienced pilots to help work out operational procedures for the newer aircraft. Hartwell spent 6 months at Muroc Army Airfield in California, flying test missions in early model Liberators, documenting performance characteristics, and helping write the technical manuals that would guide combat operations. The B-24 Liberator was a controversial aircraft in 1943. It could fly higher, faster, and farther than the B-17 Flying Fortress, carrying a heavier bomb load with greater fuel efficiency. Its Davis wing design was aerodynamically superior, providing exceptional lift-to-drag ratio that translated into impressive range. But pilots who had flown Fortresses complained that the Liberator was harder to fly, less stable in formation, and more vulnerable to battle damage. The B-24's high-mounted wing gave it a reputation for being unforgiving in emergency situations. Its tricycle landing gear was modern but required different techniques than the taildragger configuration of the B-17. The Liberator was faster, but speed came at the cost of the solid, stable bombing platform that made the Fortress so effective. During his months at Muroc, Hartwell developed a deep understanding of what the B-24 could and could not do. He learned how to trim the aircraft for long-range cruise, how to manage engine temperatures during formation flying, how to handle the tricky landing characteristics that had killed several inexperienced pilots. He also began to question some of the official specifications, particularly regarding bomb loading. The bomb bay of the B-24 was different from the B-17's. The Liberator's bay was longer and featured a unique rolling bomb door system that opened like a roll-top desk rather than splitting down the middle like the Fortress. This design reduced drag when open, which should have made it superior for bombing. But the internal configuration seemed inefficient to Hartwell. The vertical shackle mounting left significant empty space in the bay. The bombs hung nose up, which was necessary for safe separation, but the arrangement seemed to waste volume. During test missions, Hartwell began calculating alternative configurations. What if bombs could be mounted horizontally instead of vertically? What if smaller bombs could be nested more densely? What if the weight distribution assumptions that govern current loading procedures were overly conservative? He raised these questions with engineering officers at Muroc, but received polite dismissals. The current bomb loading procedures had been established by Consolidated Aircraft's engineers based on extensive testing. Changing them would require recertifying the aircraft's structural integrity, revising technical orders throughout the entire bomber fleet, and retraining thousands of ground crews and bombardiers. The war effort was already straining industrial and training capacity. Nobody wanted to introduce complications based on theoretical improvements from a captain who had never flown a combat mission. Hartwell arrived in England in December 1942 with his theories unproven and his suggestions ignored. He was assigned to the 44th Bomb Group at Shipdham, given a crew, and told to focus on surviving his 25-mission tour. The 44th was known as the Flying Eight Balls, taking their name from the group's tail markings that featured a large circle 8. They had been the first B-24 group to arrive in England, flying their first mission in November 1942. By the time Hartwell joined them, they had flown enough missions to understand that strategic bombing over Germany was proving far more difficult than pre-war theorists had predicted. The Norden bombsight, which was supposed to enable precision strikes from high altitude, worked well in clear conditions, but Europe was rarely clear. Cloud cover obscured targets. Smoke from earlier bomb hits drifted across aim points. German fighters attacked during bomb runs, forcing evasive action that disrupted careful approaches. Anti-aircraft flak created turbulence that threw off final adjustments. And even when conditions were perfect, even when bombardiers achieved direct hits, the destruction caused by 8,000 pounds of bombs was often insufficient to neutralize industrial targets that were larger, more dispersed, and more heavily constructed than planners had anticipated. The problem was simple mathematics. A factory complex covering several acres required multiple direct hits to be effectively destroyed. A single B-24 carrying 8,000 pounds could crater the ground, collapse some buildings, and disrupt operations temporarily, but German repair crews proved remarkably efficient at restoring production. Large-scale destruction required multiple aircraft striking the same target, but formation bombing was inherently imprecise. Bombs released from different aircraft in formation fell in patterns that spread across hundreds of yards. Some struck the target. Many did not. The Army Air Force's solution was to send more aircraft on each mission. If individual bomb loads were insufficient, increase the number of bombers. But aircraft production was limited. Crew training took months. Losses over Germany were mounting. Every bomber shot down represented an enormous investment in material and human resources lost. The strategic bombing campaign was becoming a war of attrition that America was not clearly winning. Preparing and narrating this story took us a lot of time, so if you are enjoying it, subscribe to our channel, it means a lot to us. Now back to the story. Hartwell flew his first combat mission on January 3, 1943, a raid against the submarine pens at Saint-Nazaire on the French coast. His B-24, christened Dakota Queen by her original crew, carried 8,000 pounds in standard configuration. The mission was considered relatively easy by the standards of early 1943. The target was on the coast, reducing flight time over enemy territory. Fighter opposition was light. The concrete submarine pens proved nearly impervious to bombing. Hartwell watched through the flight deck windows as hundreds of bombs from multiple groups struck the target area, raising enormous columns of smoke and debris. When reconnaissance photos came back 3 days later, the submarine pens were undamaged. The concrete shelters protecting German U-boats were too thick for general-purpose bombs to penetrate. The mission had cost the 8th Air Force 4 aircraft and 40 men killed or captured. The submarines continued operating without interruption. Over the following weeks, Hartwell flew missions to targets across occupied Europe and Germany. He bombed railroad marshalling yards at Hamm, industrial facilities at Wilhelmshaven, and aircraft factories at Ostersleben. Each mission reinforced the same frustrating lesson. The bomb loads his aircraft carried were insufficient to guarantee target destruction. On several occasions, his crew achieved excellent bombing accuracy, placing their ordnance directly on the aim point, only to see reconnaissance photos reveal that the target remained operational. German factories were large, robust structures with redundant equipment and dispersed production lines. Cratering part of a factory complex did not stop production when machinery could be moved to undamaged sections and operations continued while repairs proceeded. The psychological impact of these missions on bomber crews was significant. Men risked their lives flying through flak and fighter attacks, executed perfect bombing runs, and watched their efforts produce minimal lasting effect. The knowledge that their sacrifices were not decisively damaging the German war machine created a sense of futility that eroded morale more effectively than enemy action. Hartwell began discussing the problem with his bombardier, Frank Chen, during the long flights to and from targets. Chen was a mathematics graduate from Berkeley who had trained at Midland Army Airfield in Texas before being assigned to the 44th. He was precise, analytical, and shared Hartwell's frustration with the limitations of current bombing procedures. During flights, while other crew members dozed or smoked or tried not to think about the fighters and flak ahead, Hartwell and Chen calculated. They estimated the volume of the bomb bay. They measured the dimensions of different bomb types. They calculated weight distributions for alternative loading configurations. They reviewed the physics of bomb separation and the aerodynamics of release sequences. The conversations were theoretical, mental exercises to pass the time during 6-hour missions to Germany and back. Neither man seriously believed they could change established procedures. But the calculations were intriguing. The standard vertical loading configuration in the B-24 bomb bay left substantial empty space. Bombs hung nose up on shackles, separated by intervals that ensured safe release. But what if the intervals could be reduced? What if bombs could be loaded horizontally, stacked more densely? The bomb bay was approximately 10 feet long and 4 feet wide. Current procedures used less than 60% of that volume. If bombs could be nested more efficiently, the bay could potentially accommodate substantially more ordnance. The weight limit was 8,000 pounds for long-range missions, but that limit was based on fuel load requirements for reaching distant targets. For shorter-range missions, the aircraft could carry more weight because less fuel was needed. The B-24's maximum takeoff weight was 65,000 pounds. Empty weight was about 37,000 pounds. That left 28,000 pounds for crew, fuel, ammunition, and bombs. On maximum range missions, fuel alone could weigh 16,000 pounds, leaving room for only 8,000 pounds of bombs. But on shorter missions requiring only 8,000 pounds of fuel, the weight available for bombs doubled. The question was whether the bomb bay's structure could handle the increased load and whether bombs could be physically fitted into the bay at higher density. On February 10, 1943, Hartwell's crew flew a mission to the railway yards at Ghent, Belgium, a relatively short flight that required less than half the fuel needed for deep penetration raids into Germany. After landing back at Shipdom, Hartwell asked Chen a hypothetical question. If they had only needed half fuel load, could they have carried double the bombs? Chen thought for a moment, then shook his head. The bomb bay's shackles were fixed for standard loading. Without modified hardware, there was no way to mount additional bombs. But what if we changed the hardware? Hartwell asked. Chen's expression shifted from dismissal to consideration. Theoretically possible, he said slowly. But nobody's going to authorize modifications based on theory. We'd need to prove it works. How do we prove something when we're not allowed to try it? Hartwell asked. Neither man had an answer, but the question stayed with them. The opportunity came from an unexpected direction. On March 1, 1943, Colonel Leon Johnson assumed command of the 44th Bomb Group. Johnson was a career officer who had graduated from West Point in 1926, flew bombers in the peacetime army, and possessed the rare combination of respect for established procedures and willingness to consider innovations that improved combat effectiveness. Unlike some commanders who viewed any deviation from doctrine as dangerous freelancing, Johnson understood that war created situations that textbook solutions could not address. During his first week at Shipdom, Johnson held individual meetings with his aircraft commanders, asking each pilot about their experiences, their concerns, and their suggestions for improving operations. When Hartwell's turn came, he almost held back the idea that had been consuming his thoughts for weeks. But Johnson asked directly if Hartwell had any recommendations for increasing the group's combat effectiveness, and something in the colonel's expression suggested genuine interest rather than pro forma inquiry. Hartwell explained his observations about bomb bay volume utilization. He described the calculations he and Chen had performed. He outlined the theoretical possibility of doubling bomb loads on short-range missions by reconfiguring shackle arrangements and loading bombs more densely. He acknowledged that the idea contradicted established procedures and would require engineering approval. He expected Johnson to thank him politely and move on to the next pilot. Instead, Johnson leaned forward and asked how Hartwell proposed to test the theory. The question caught Hartwell off guard. He stammered something about needing approval from higher headquarters, about structural testing requirements, about the complexity of modifying technical orders. Johnson cut him off. Testing doesn't require changing technical orders, the colonel said. Testing requires one aircraft, a maintenance crew willing to try something different, and a pilot willing to fly it. The question is whether you're that pilot. Hartwell said yes before his caution could override his conviction. Johnson nodded. You have 2 weeks, the colonel said. Work with the group engineering officer. Figure out if your theory is physically possible. If it is, we'll fly a test mission to a close target with double the standard bomb load. If the aircraft handles the weight and the bombs release cleanly, I'll take it to division. If it doesn't work, we forget it and you go back to flying standard missions. Clear? Hartwell confirmed. Johnson stood, signaling the meeting's end. But as Hartwell reached the door, the colonel added one more thought. Captain, if this works, you're not just increasing one cruise bomb load. You're potentially changing how we fight this war. The pressure of that responsibility is considerable. If you'd rather not carry it, now's the time to say so. Hartwell met Johnson's gaze. I believe it'll work, sir. Then make it work, Johnson said. The next 2 weeks became an intensive collaboration between Hartwell, Chen, and the 44th Bomb Group's engineering section. The group's engineering officer was Captain Raymond Kowalski, a mechanical engineer from Pittsburgh who had worked at Westinghouse before the war designing industrial machinery. Kowalski was skeptical but methodical. He listened to Hartwell's theory, reviewed Chen's calculations, and then spent 2 days crawling through the bomb bay of Dakota Queen with measuring tapes, calipers, and structural diagrams. His preliminary conclusion was cautious. The theory wasn't obviously impossible, but testing would require fabricating custom shackle assemblies that could mount bombs horizontally and in tighter spacing than standard vertical racks allowed. The modifications would take time and would be irreversible. If the test failed, Dakota Queen's bomb bay would be non-standard, potentially grounding the aircraft until factory standard equipment could be reinstalled. Johnson approved the work anyway. Kowalski's team worked 12-hour shifts in the maintenance hangar, fabricating new shackle assemblies from steel stock and hydraulic fittings. The design they developed was ingenious in its simplicity. Instead of vertical racks holding bombs nose up, they created horizontal cradles that held bombs on their sides. The cradles were arranged in 3 tiers, stacked vertically to utilize the bomb bay's height. Each tier could hold 6 500-pound bombs, positioned lengthwise along the bay. The total capacity was 18 bombs instead of the standard 16, but more significantly, the tighter packing left room for additional small bombs in the spaces between the main load. By filling those gaps with 100-pound incendiaries, the total load could reach 9,500 pounds while still maintaining the 8,000-pound weight limit when the incendiaries were excluded. For a short-range mission where fuel weight allowed higher bomb loads, the entire capacity could be loaded, reaching 12,000 pounds. The structural concern was whether the bomb bay doors and internal bracing could handle the concentrated weight. Kowalski calculated stress loads using formulas from his Westinghouse days, comparing the distributed weight of the modified configuration against the bay's design specifications. His conclusion was that the structure should hold, but should was not the same as wood. On March 13, the modifications were complete. Dakota Queen sat on the hardstand with her bomb bay loaded according to the new configuration. 18 500-pound general-purpose bombs lay horizontally in their custom cradles, along with 2,400-pound incendiaries tucked into the remaining spaces. The total load was 11,400 pounds, 43% more than the aircraft had ever carried before. The ground crew had loaded the bombs carefully, distributing weight to maintain proper center of gravity. Kowalski had personally checked every shackle, every hydraulic line, every safety mechanism. Chen had calculated the release sequence to ensure proper separation. Everything looked correct on paper. But paper calculations and reality were different things, and the only way to know if the system worked was to fly it. Hartwell walked around Dakota Queen that afternoon, running his hand along the fuselage, checking the bomb bay doors from outside, trying to visualize what would happen when those doors rolled open at 10,000 feet and 12,000 pounds of explosives dropped free. His crew gathered around the aircraft, unusually quiet. They understood the risk. If the modified shackles failed, if bombs collided during release, if the aerodynamics of the overloaded configuration destabilized the aircraft, they could die testing an idea that challenged everything the Army Air Forces had certified as safe. Technical Sergeant Paul Morrison, the flight engineer, voiced what everyone was thinking. "Captain, if this goes bad, we're not going to have time to bail out." Hartwell nodded. "I know. If any of you want to sit this one out, I'll find volunteers." Nobody moved. After a moment, Chen spoke. "We've done the math. It'll work." Morrison snorted. "Math doesn't stop falling bombs from hitting each other." "True," Chen admitted. "But the math says they won't hit each other if we release them in the right sequence." "So let's get the sequence right," Hartwell said. Colonel Johnson scheduled the test mission for March 15. The target was the railway marshalling yard at Dunkirk, France, a short flight across the English Channel that would require minimal fuel and allow Dakota Queen to carry the full experimental load. Only one aircraft would fly the mission, which violated normal procedures that required bombers to fly in formation for mutual protection. But Johnson had obtained fighter escort from an RAF Spitfire squadron based in Kent, and the short distance meant Dakota Queen would spend less than 30 minutes over occupied territory. The mission was officially classified as a special weapons test, which gave Johnson cover if higher headquarters questioned why he was flying single aircraft missions against minor targets. The real test would come when the bombs released. If they dropped cleanly, if the aircraft remained controllable, if the load hit the target, the test would succeed. If any of those factors failed, men would probably die, and the theory would die with them. March 15 dawned clear and cold. Ground crews fueled Dakota Queen and loaded the modified bomb bay under Kowalski's supervision. Each bomb was positioned exactly according to the loading diagram Chin had prepared. The shackles were checked and rechecked. The hydraulic release mechanisms were tested without ordnance, then tested again with the full load installed. Everything functioned correctly, but ground tests with stationary aircraft revealed nothing about how the system would perform in flight. At 0815 hours, Hartwell and his crew completed the pre-flight briefing. The operations officer reviewed the route, the altitude, the timing. The intelligence officer confirmed that German fighter activity in the Dunkirk area had been light recently. The weather officer predicted excellent visibility. Everything seemed designed to make the mission as simple as possible, which made Hartwell more nervous rather than less. Simple missions could still kill you if something unexpected went wrong, and they were about to do something nobody had tried before. At 0900 hours, Hartwell advanced the throttles and Dakota Queen rolled down Shipton's runway. The takeoff run was longer than normal. The overloaded aircraft was sluggish, requiring most of the runway's length before the nose wheel lifted. Hartwell held the bomber low, building speed gradually before attempting to climb. The extra weight made the aircraft feel different, heavier on the controls, slower to respond to inputs. Morrison called out airspeeds and engine temperatures from the engineer's station. Everything stayed within normal ranges, but barely. As they climbed through 5,000 feet, Hartwell felt the aircraft settle into something resembling normal flight characteristics. The modified bomb load was within the B-24's structural capacity, but it was definitely at the edge of that capacity. The flight across the channel took 20 minutes. The RAF Spitfires joined formation over Dover, 3 fighters positioning themselves above and behind Dakota Queen. The English coast fell away, replaced by grey water. Then the French coast appeared ahead, and Hartwell turned toward Dunkirk. Anti-aircraft fire began appearing around them as they approached the target, black puffs of smoke marking near misses. The bombardier called out his approach. Chen's voice was steady, professional, hiding whatever nervousness he felt about being the first person to attempt releasing bombs from the experimental configuration. At 10,000 feet, Dakota Queen leveled off. Chen activated the bomb bay door controls. The unique rolling doors opened, and Hartwell felt the aircraft shudder as the airflow changed. This was the critical moment. If the bomb load shifted, if shackles failed, if anything went wrong, they would know immediately. The aircraft remained stable. Chen began the release sequence he had carefully planned, dropping bombs in a specific order designed to maintain balance and prevent collisions. Hartwell felt each release through the controls, a slight lurch as weight dropped away. The sequence took 12 seconds, far longer than a standard release. Then Chen announced bombs away, and Dakota Queen suddenly felt light, responsive, alive in ways she had not felt since takeoff. Hartwell banked away from Dunkirk, turning toward the channel and home. Behind them, the marshalling yard disappeared in erupting explosions. The bombs had released cleanly. The aircraft had remained controllable throughout the drop. The mission, from a technical standpoint, was a complete success. But the real test would come from the reconnaissance photos. If the increased bomb load had produced proportionally increased destruction, the test would prove Hartwell's theory. If the damage was equivalent to what a standard load would have achieved, then carrying extra bombs was pointless risk. Dakota Queen landed back at Shipton at 1,115 hours. Colonel Johnson was waiting on the hardstand when Hartwell shut down the engines. "How'd she handle?" Johnson asked. "Heavy on takeoff," Hartwell replied. "Stable in flight. The bombs dropped clean." Johnson nodded. "Now we wait for the photos." The reconnaissance aircraft flew over Dunkirk that afternoon, photographing the results of Dakota Queen's mission. The photos arrived at Shipton by courier that evening. Johnson, Hartwell, Chen, and Kowalski gathered in the operations office to review them. The intelligence officer spread the photographs across the table. The Dunkirk marshalling yard was a moonscape. The concentrated bomb load from a single aircraft had cratered the rail lines across 300 yards, collapsed several buildings, and destroyed dozens of rail cars. For comparison, the intelligence officer pulled photos from a previous mission where 3 B-24s with standard loads had struck the same target. The damage from Dakota Queen's single sortie exceeded the combined destruction from 3 aircraft carrying standard loads. The math was undeniable. Hartwell's modified configuration had delivered 43% more ordnance and produced damage that appeared nearly 3 times more effective because the concentrated drop pattern placed bombs closer together, multiplying destructive effects. Johnson studied the photos in silence for a full minute. Then he looked at Hartwell. "You've just changed everything," the colonel said quietly. "Starting tomorrow, I want Kowalski's team to begin modifying every aircraft in this group. We'll work out the details as we go, but the principle is proven. Captain, you've given us a weapon the Germans won't see coming." Hartwell felt the weight of that statement settle over him like a physical burden. Because increasing the bomb load capacity of the 44th Bomb Group was just the beginning. If the modification worked for one group, it would work for every B-24 group in the 8th Air Force. And if it worked in Europe, it would work in the Pacific. The technique Hartwell had pioneered in Dakota Queen's Bomb Bay represented a force multiplier that would ripple through the entire strategic bombing campaign. But force multipliers attracted attention, and attention brought pressure, and pressure could kill as surely as flak or fighters. Hartwell had just made himself and his crew important in ways that had nothing to do with survival and everything to do with proving that the impossible was merely difficult and the difficult merely required willingness to question assumptions that everyone else accepted as unchangeable truth. The story of what happened over the next 6 weeks would become legend in the 8th Air Force, though much of it would remain classified for years after the war ended. But in that moment, standing in the operations office looking at reconnaissance photos that showed devastation from a single aircraft carrying bombs that weren't supposed to fit in her bay, Hartwell understood that his war had just become vastly more complicated and exponentially more dangerous. The Germans were about to learn that American bombers could hit harder than their intelligence estimates had predicted, and when they learned that lesson, they would do everything in their power to destroy the aircraft and crews making it possible. Within 72 hours, Kowalski's maintenance crews began converting every flyable B-24 in the 44th Bomb Group. The modifications spread like fever through Shipdom's maintenance hangars. Crews worked through nights, fabricating horizontal bomb cradles from steel stock, installing custom shackles, testing hydraulic release mechanisms until their hands were raw. By March 22, 12 aircraft had been modified. Colonel Johnson scheduled the first group mission using the enhanced configuration for March 24 against the Ruhr Valley Industrial Complex, the heart of German steel production that crews grimly called Happy Valley for the murderous flak concentrations that defended it. The target was the Krupp Steelworks at Essen, a sprawling facility that had absorbed multiple raids with minimal lasting damage. Previous attacks by 30 aircraft carrying standard loads had cratered yards and collapsed some buildings but never achieved sustained production disruption. German repair crews restored operations within days. Johnson's plan was audacious. 12 modified B-24s would strike Krupp with the destructive power of 18 standard bombers. If the concentrated assault overwhelmed repair capacity, if the damage proved catastrophic rather than temporary, the raid would validate Hartwell's technique on a strategic scale. If it failed, if the modifications caused problems in combat conditions, if German fighters exploited the experimental formations, 12 crews might not return. Hartwell flew as mission commander on March 24, leading the formation through heavy clouds over the North Sea. The weather was terrible, which meant German fighters would be grounded but also that bombing accuracy would suffer. They reached Essen through gaps in the clouds, and anti-aircraft fire erupted around them like black flowers blooming in instant violence. The flak was worse than Hartwell had ever experienced, dense enough that collision with shrapnel seemed inevitable. 2 aircraft took hits during the bomb run. Dakota Queen shuddered as fragments punched through her skin, but nothing vital was struck. Chen released their 12,000-pound load, and 11 other bombardiers did the same. 144,000 pounds of explosives fell on Krupp in 90 seconds. The formation turned for home through a gauntlet of flak that seemed determined to exact payment for the destruction below. One aircraft fell out of formation trailing smoke, her number 3 engine shredded by direct hit. The pilot, Lieutenant Robert Hayes, fought to maintain altitude as the bomber lost speed. Hartwell watched helplessly as Hayes coaxed his crippled aircraft across the Dutch coast before the second engine failed. The crew bailed out over the North Sea. RAF Air Sea Rescue picked up 6 of the 10 men. Hayes and 3 others were never found. The victory at Essen came with that familiar bitter cost, but the reconnaissance photos showed devastation that exceeded anything previously achieved against the Krupp complex. German intelligence analysts examining the damage were baffled. The crater patterns indicated bomb loads far exceeding known B-24 capacity. Initial reports were dismissed as observational errors. When subsequent raids produced similar results, German high command realized American bombers had somehow increased their destructive capacity by factors that made existing defensive calculations obsolete. Flak concentrations that had been calibrated to inflict acceptable losses against standard formations now faced bombers delivering substantially more ordnance per sortie. The strategic mathematics of attrition warfare had shifted against Germany. Word of the 44th's enhanced bombing capacity reached 8th Air Force headquarters by early April. General Ira Eaker, commanding the 8th, visited Shipdom to observe the modifications personally. After reviewing damage assessments and loss rates, Eaker authorized immediate implementation across all B-24 groups. By May 1943, every Liberator group in England was adopting variations of Hartwell's horizontal loading technique. Engineering teams refined the design, standardizing components, and streamlining installation. What had begun as experimental modification in one aircraft became theater-wide doctrine within 8 weeks. The strategic impact became measurable by summer. Targets that had required multiple missions to neutralize were being destroyed in single raids. German industrial production faced sustained disruption rather than temporary setbacks. Repair capacity was overwhelmed by the sheer volume of destruction concentrated in individual attacks. The 8th Air Force's effectiveness per sortie increased dramatically even as aircraft numbers remained relatively constant. Hartwell continued flying missions through his 25-sortie tour, which he completed in June 1943. His final mission was a return to Krupp, where the steelworks he had first struck in March remained partially inoperative 3 months later, unable to recover from the cascade of damage that enhanced bomb loads had inflicted. The technique spread beyond Europe. Pacific Theater B-24 groups adopted horizontal loading for strikes against Japanese industrial targets. The modifications proved equally effective against different target types and operational conditions. By war's end, the enhanced bombing capacity Hartwell had pioneered was credited with accelerating the strategic bombing campaign's effectiveness by an estimated 6 months, achieving destruction levels that would have otherwise required thousands of additional sorties and hundreds more aircraft lost. Hartwell survived the war, promoted to major and awarded the Distinguished Flying Cross for his innovations in bombing tactics. He returned to Duluth, where he worked in his father's fishing business and rarely spoke about his wartime service. The classified nature of the bomb loading modifications meant few outside military circles understood what he had accomplished. When the techniques were finally declassified in the 1960s, historians recognized Hartwell's contribution as among the most significant tactical innovations of the strategic bombing campaign. A single captain's willingness to question established procedures had multiplied American bombing effectiveness at precisely the moment when strategic air power's value was being questioned. The lesson extended beyond technical innovation. Hartwell had demonstrated that institutional assumptions could be challenged when evidence supported alternatives. His methodical approach, grounded in practical calculation rather than reckless experimentation, showed how careful analysis could reveal capabilities hidden within existing systems. The bombs had always fit. The aircraft had always possessed the structural capacity. The potential had always existed. What was required was someone willing to measure carefully, calculate precisely, and prove through demonstration rather than argument that better methods were possible. The modified B-24s flew on through 1945. Their enhanced capacity becoming so routine that crews forgot the technique had once been considered impossible. That transformation from revolutionary to routine represented Hartwell's most lasting achievement. He had not merely increased bomb loads. He had expanded what combat crews believed their aircraft could accomplish, and that expansion of possibility proved as valuable as any physical modification to steel and hydraulics. Up next, you've got two more standout stories right on your screen. If this one hit the mark, you won't want to pass these up. Just click and check them out.